And hello to all our listeners. Thank you for joining us today. I'm delighted to be back with you for another segment on green chemistry and sustainability, brought to you by the ACS and the Green Chemistry Institute. I have been at the Institute for 4 years now, and I've seen amazing progress in the awareness and the adoption of green chemistry over that time. But make no mistake, we have a very long way to go before green chemistry and green engineering are routinely employed in the design and development of new chemicals, materials, and the processes to make them. It's the mission of the ACS Green Chemistry Institute to catalyze and enable the implementation of the principles of green chemistry and engineering throughout the global chemical enterprise. With that mission in mind, we have many programs including industrial and academic training and workshops geared to all levels from beginners to advanced practitioners, industrial roundtables, our annual Green Chemistry and Engineering Conference, the recently released American National Standards Institute Standard for Greener Chemical Information, our Green Chemistry Summer School, and I'm delighted to say we've just recently launched a scholarly network to build the communication bridge between the green chemistry community and the business schools who train our future decision makers. That's just a quick snapshot of our program, so I hope you will visit our website for a more complete listing and information. John?
Great. Well, thank you, Bob. Thanks for providing that introduction. Go ahead and take it away for us on the session.
All right. Thanks again, John. I'm delighted to be here, as I said earlier. During today's presentation, Dr. David Constable will discuss measures of green chemistry performance. Today, you're going to hear about key drivers for green chemistry metrics, how to build green chemistry metrics into synthetic route and chemical process design, how to create a business process for incorporating green chemistry metrics, and most importantly, how to choose the right metrics, because not all metrics are worth collecting. Before we get started, it's my pleasure to introduce to you our speaker. Dr. David Constable is a well-recognized expert in the area of green chemistry, green engineering, and life cycle analysis. In fact, he is an early pioneer of the application of these tools beginning in the pharmaceutical sector. As you saw earlier, he is also the co-author of the recently published book, Green Chemistry and Engineering, A Practical Design Approach. Most recently, David was the Corporate Vice President of Energy, Environment, Safety, and Health for Lockheed Martin Corporation. Prior to joining Lockheed Martin, he was the Director of Operational Sustainability in the Corporate Environment, Health, and Safety Department at GlaxoSmithKline. In addition to his book, David has authored or co-authored more than 28 journal publications. David has said, the intersection of corporate sustainability, smart business practices is a crossroads. Companies can no longer afford to avoid on the path to increased productivity and reduced cost. An effective plan puts the roadmap to reach goals which benefit both the environment and the bottom line. I think you would agree the role of metrics is part of any roadmap.
Okay. Hello, everybody. This is David Constable. It's a real pleasure for me to be here this afternoon, and I hope that everyone can hear me well, and if not, please let us know. I wanted to say right at the outset that I think green chemistry metrics are a great driver of innovation and opportunity. Really, they help us to point out things that we may not see otherwise. They help us to drive in areas where we may not have thought about in the past. And I'm hoping that in the discussion we have today, I can be a little bit provocative and bring some ideas across to you that you may not have seen before. There's lots of opportunity for discussion at the end of this. I will breeze through a lot of these, but certainly you can continue to provide Bob questions as we go through. So in today's discussion, I'd like to talk a little bit very briefly about some sustainability risks, and I'm sure that most of you, if not all of you, are familiar with the idea of sustainability. And my focus is really going to be about sustainability from the chemical processing industries and mostly around the batch chemical operations. So your fine chemicals, specialty chemicals, and pharma industries. But what I would say is those risks are really applicable in many other industries as well. I'd like to spend a little bit of time talking about the current situation, and see the tagline that it was. I've been thinking about green chemistry for quite some time, and if you look at the evolution of green chemistry, there has been a lot of progress that's been made, but we're really fighting an uphill battle against a lot of in-ground existing technology and a lot of practices that we find in the common everyday practice of green chemistry. The next idea I'd like to get across is really about how important design is. And if you don't build green chemistry in from fundamentals, it's really about how you think about the problem that we want to try and get across. And if you're not thinking about it right up front, at the very beginning of the conceptualization phase, then you're never going to get it right. You can't build this in or bolt it on at the end. I'd like to talk about very briefly about establishing the right process. And I'll have a lot more to say about it, but it really doesn't matter what that process is. But I'm a process-oriented person, and I think that processes help us tremendously in providing a certain amount of discipline. Choosing the right metrics is the next area I'd like to spend a few minutes about. And as you'll see from the graphics, there's a lot of different metrics that have been discussed almost immediately. And choosing the right ones is extremely important to drive the right behaviors, because again, what we ultimately want to do is to change the behaviors that our chemists and our engineers. And finally, just end on a positive note that I'm quite confident that the positive change is absolutely possible. I would like to launch into a poll, and I'm going to turn this over to Bob. So, by the way.
So thank you, David. Thank you, David. We apologize for the audio. We know some of you are having problems. If it's convenient, perhaps you can look on your panels on your screen and dial in. But let's go with our poll. How many of you use these metrics? Please feel free to select all that apply: yield, chemical efficiency, selectivity, atom economy, other, or you don't use any of these. And we'll close the poll in 5, 4, 3, 2, 1. The poll is closed. We can see the results. Well, it turns out, not surprising, many people use the yield metric, which is 64% of those who responded. Chemical efficiency and selectivity at 51%. About a quarter of our audience uses atom economy, and about a quarter of our audience either uses some other metric or no metric at all. So, David, back to you.
Helps if I unmute. Great results, Bob, and thanks so much, everybody, for doing that. We'll talk about some of these measures, and it's great to see that most of you are using one form of metric or another, and that's a good thing. So let me do this on to the next slide. So many people, when they think about metrics, and metrics of any kind, sort of take this approach that you'll see on your screen, where they say, well, the population of Pineview was established in 1872, and it has a population of 732 and an elevation of 5,000 plus feet. So we'll total that up, and that's the answer, and that's our metric. And point is that we many times take completely disparate approaches or ideas, total them up, and try and come up with some measure of how we're doing. And I would argue that that's really not the approach that we want to take. So we go on to, let's see, a little bit slow system here. All right, so what this leads to many times is the fact that people end up just calling something green because they've selected one measure, say for example it's derived from renewable feedstocks, and therefore it's green, when in fact it may not be. And we really want to try and avoid that. The other idea that I wanted to put out there about metrics is the importance of using metrics. Because if we don't keep score, if we're not continually measuring, then we're only practicing. And that's not good. So the next thing I wanted to get across is about asking the right questions. And it's extremely important that no matter what you do, whether it's something else, ask the right kind of answer to one question. So let's move on and talk a little bit about sustainability risks. And I'm, again, mainly focusing in on the entire chemical enterprise and specifically in the batch chemical operations enterprise. First thing, obviously, if you look at chemicals, is that the feedstocks are petroleum-based. Yes, we're making a slow transition into renewables, but it is a slow transition, and it's really in just high-value added materials. So we really do need to think about how we can transition to different kinds of feedstocks. Historically, outside of the petrochemical industry, which is generally very efficient, we find very poor overall process efficiencies, and this is true of both mass and energy. The next thing is that there's a lot of data which is missing, and this is really what has given rise to things like REACH legislation, the desire to change the TSCA regulations in the United States, the California green chemistry, really focusing on how can we do a better job at getting information about the chemicals that we're using into common use. The next thing I wanted to talk about is high hazard materials. And we still make use of many high hazard materials. We do this for a lot of reasons, because they work, and they work very well. And so we end up continuing to use them. The other thing that we do is we make use of a lot of high risk chemistries. And clearly we know we can engineer out risk in many cases, and we end up using process chemistries. But it's far better for us to not have highly hazardous materials to begin with. The other thing is that we make use of inappropriate engineering or process controls in some cases, and these lead to problems in manufacturing processes. Also have issues with human and environmental experts. We can imagine a future regulations, and we constantly have to work around those. So let's talk a little bit about the current chemical process, batch chemical process situation. It's clearly a very complicated situation. We contend with very large portfolios of products in multipurpose plants. We have a significant amount of route and process modification that requires, in some cases, complete substitution. We have to analyze those chemical processes, and that is takes time, and it's oftentimes a fairly expensive process. And there's a focus on cost of good and good measures of our process. So one of the things I wanted to have everyone think about a little bit, I need to dial in by phone. Okay, everybody hang on, and I will dial in by phone.
David?
Hello.
Hi, David. This is John Christensen. On your GoToWebinar
Yes.
control panel, you need to select telephone in the audio box. Otherwise, we'll get an echo feedback.
I don't see the telephone audio box.
Okay, go to your GoToWebinar control panel. There should be a
Okay,
box labeled audio. Select telephone now.
Okay, got telephone. All right, there we go. How's this? Can you hear me? Hello?
Yes, we can hear you. Okay, I'm transferring the screen back over.
Okay, can folks hear me?
Yes, we can hear you, David.
And okay, should I back up?
I think keep going.
Okay. So apologies for that technical difficulty there with the audio. And hopefully, as we go forward, folks will hear better. First thing I wanted to talk about in this slide is really about chemists using ancient chemistries. And if you look at randomly selecting 100 chemistries in a review recently, 54% of the chemistries were created or developed, discovered before World War I. 74% were discovered before World War II, and 91% were discovered before 1975, with only 9% discovered during the 1990s. So what does this tell us? It tells us that chemists, by and large, need to change the types of chemistries that are in their toolbox. That's where we need to get to. Let's think for a moment about technology. And here again, things really haven't changed. We could do an exercise, and I could ask, when do you think the batch reactor came into being? And it actually came in the Bronze Age. And if you take this slightly recent view of a chemical operation in the Middle Ages, you'll notice that there was batch reactors. There's impellers for mixing in those batch reactors. And if you look closely at that impeller, you would know that things haven't changed that much even to this day. They look very much that way. If you take distillations, a commonly used process, clearly that's been around for a very long time. And salt crystallization, another thing that was done a very long time ago, beginning in the Bronze Age. Clearly, the issue is not in new ideas, but in escaping the older ones. I'm not sure if we're still having an audio problem or not, but I'll continue on. Next thing is around design, and really this quote from Bill McDonough about design being a signal of intention. It's extremely important that we design green chemistry. We design green into the chemistries that we do. So that takes us to our next poll, and I'm going to turn it back over to Bob. Bob?
Well, thank you, David. And again, I want to acknowledge for all our listeners, thank you so much for your patience because we've had some challenges here. So our second poll question is, how important do you think design is in ensuring a sustainable chemical route or process? Please select one of the four: very important, important, moderately important, or a waste of time. And we'll close the poll in 5, 4, 3, 2, 1. And the poll is closed. Wow, okay, so David, this is an interesting result. It looks like about 79% of our audience feel the answer is very important. Another 18% say important. So that's almost 100%. Then back to you, David.
Fantastic. And I'm delighted to see that everybody thinks that designing these things in is extremely important, because I couldn't agree more.
So let's move on and talk about how we design it in. First of all, we need to do the design from the ground up, as I mentioned in the very beginning of my introduction. If we don't build it in from day one, it isn't going to be there. We can't bolt it on after the fact. The next thing, we need to think differently about what we're doing in R&D and how we're doing it. Again, if you think about the chemistries and the technologies, clearly these things have to change. We have got to put a different set of tools into the hands of chemists and engineers so that from day one we can do the research and development in a different way. We need to make sure that the tools that we need are easily accessible and available to everybody that needs them. So we're constantly confronted with a variety of problems when we try and do green chemistry. And it's a balance. It's a balance that we fight. First of all, there's a lot of money to be had. If you think about pharmaceuticals and other high value-added products, there's a lot of money on the table to bring a product to market. And that's true pretty much of any industry. So we have to think about how we can green the process design early when the relative cost is much lower. And we have to balance that with our continual pressure from the commercial side to bring things in as quickly as possible. And the problem with that, particularly in pharma, but certainly in other industries, is that products have a habit of going away very quickly before they make it to market. So it is a balancing act, and it's a difficult one. And clearly, I'm not intending or attempting to minimize just how difficult it is to do this. The next thing I'd like to talk about is really the necessity to establish the right process. And the right process can be a simple one. And not only should it be a simple one, but it should be something that fits in, is part of, or can be embedded as part of a normal way of working. Because if you're asking chemists and engineers to do something that's radically different, they really don't have enough time. They've already got a lot of things on their plate. Within one of my former companies in GlaxoSmithKline, we used what was known as a process-related material review. You can call it whatever you want to do or however you want to designate it. But the main issue is that you want to be able to highlight key sustainability issues for both the materials and the process as quickly as you can. You want to be able to complete assessments at known stages of development. Surely most people use some kind of stage gate process. We want to make sure that you document your process, and that will allow us to have discussions, and I communicate opportunities to chemists and engineers. And I think the most important thing is that in these cross-functional teams, people are making an effort to talk to one another. And unfortunately, in many companies and in academia, departments are siloed, and there isn't enough communication between them. So finding the right metrics is clearly important to us. It helps us to make objective comparisons. We want to be able to benchmark our progress. We want to use those metrics to drive change, and we want to be able to demonstrate improvements. And the other thing, which is extremely important in this day and age, is to increase the level of transparency that we have into our processes. Many of you are familiar with the principles of green chemistry and engineering. I would be remiss of me not to mention them, but I would just say that it's easy to simplify them. And we took the approach of bucketing them into three different areas. One was to maximize resource efficiency, the second to eliminate and minimize hazards and pollution, and thirdly, really to design systems holistically using life cycle thinking. So if you want to know more, we've published this in a book, and I'll have a visual of that later on in the presentation. So I hope I've shown that metrics are essential, and picking the key metrics is absolutely essential. Clearly, I need to have yield up there if I'm talking to a group of chemists. If not, I'd probably be lynched. Another one, which I'll talk a little bit about in a few minutes, is reaction mass efficiency. This is really about how we can change the chemistry. Another simple set of measures is the number of stages and the number of steps. I think that Paul Wender and his step economy is not looked at enough, but clearly the number of steps is a key driver in making an overall process green. So we want to think about telescoping and converging, thinking about where and when we bring in side chains, that kind of thing. Another very simple measure, and something that historically has been underappreciated, is solvents. So typically the number of solvents and the solvents per stage is a great measure for determining greenness. The other metric which you may have heard about is mass intensity, or process mass intensity, or mass productivity. It goes by a number of different names, and this is clearly about focusing on the process. And finally, there's things around materials of concern, because if we just focus on mass, we won't get the things that are hazardous, and we need to look at things from a life cycle environmental impact. Starting materials really do matter. So I told you that I'd be a little bit controversial about yield, and I would say that yield's really not a major driver of green chemistry in batch operations, and that includes what you're doing in your beaker or flask in a laboratory. Why do I say that? It's because chemists, by and large, throw away chemistries if they're not averaging 86 or 85% and above. We just switch out chemistries. And that's true of most batch chemical operations. That means that you have an overall yield for a 6-stage process on the order of 30 to 40%. If you look at the total mass that goes into that 30 or 40%, that's about 16 kilos a kilo. And even if you had 100% yield for a 6-stage process, your mass productivity would still only be about 1%. What that means is that you're throwing away 99 kilos for every kilo of substance that you're making. Therefore, I would argue that yield really isn't a very good measure for greenness. And that will take us into another poll. Bob, I'd like to turn it back over to you.
Great. Thanks, David. So our third poll question is, how many different kinds of chemistries account for 80% of all chemistries used in the pharma R&D companies? Please select one of the following: 152, 73, 512, 26, or 97. How many different kinds of chemistries account for the majority used in the pharma R&D company? And the poll will close in 5, 4, 3, 2, 1, and the poll is closed. And our results, well, we have sort of a split audience, but clearly 26 comes in at 57% of the vote. We have 8% at 152, 20% at 73, 7% at 515, and 7% at 97. So again, 57% at 26. Dave, back to you.
Well, that's a great result, and it's fascinating to me personally that a majority of you got the right answer. It's 26, and that really is an opportunity for us. It reduces the number of chemistry or chemistry targets that we have to work on, and it means that we don't we have a real opportunity or a chance to make a difference. On the next slide, I have a graphic, a pie chart, which shows some of the top chemistries that were being used in GSK between 2004 and 2005. Some of these you could argue, well, it's salt formation or, recrystallization really is not interesting or difficult chemistry, but these are the types of things that were done the most. Some couple takeaway messages is that chemistries and the mixture of chemistries change. It's really a moving target. The other thing is that with a reduced set, we can come up with that different toolbox that we need, the chemistries. So let's focus on those chemistries and change them, or change what it is that we're trying to do so that we can really make a difference. The next idea I wanted to bring about is solvent use. And in the batch operations, I don't care if it's a polymer or otherwise, you tend to have a lot of solvent. And it took us quite some time to convince folks in the pharma industry that solvents plays as much of a role as they did. And this has been validated twice now by the industry. And as you can see, that between solvents and water, you have a majority of the mass that is being used. And the interesting thing is that within GSK, about 10 solvents represented 80% of the solvent use. And solvents were the biggest contributor to process mass intensity, and they were also the biggest contributor to primary manufacturing life cycle environmental impacts. So again, point is, solvents matter. Pay attention to them. I think, in my opinion, that chemists don't pay enough to the interaction between solvents and the chemistries and the process. And that's really the benefit of having chemical engineers involved. The other thing is that there are some easy measures for determining solvents. One of them is solvent numbers, or the number of solvents, and solvents per stage. I'm just going to very quickly breeze through this, not going to spend a lot of time. Quick and dirty measure, easy to do. You can also think about scoring your solvents and basing things on environmental impact, environmental waste, the ability to recycle, incinerate, so on and so forth. You can talk about health effects. You can talk about safety. Again, you can look at these after the presentation today. It's just an idea. You can also go to the Green Chemistry Institute website under the Pharmaceutical Roundtable. There's a solvent selection guide there that's based on this particular approach. Let's talk a little bit about reaction mass efficiency. And all this is really is a combination of yield, atom economy, and stoichiometry of the reaction. And we can go on and calculate that. So for a generic reaction of A plus B going to C, clearly you can do it in terms of molecular weight, or more simply, you can just add up the masses. Mass of product C divided by the mass of A and B. Really quite a simple measure. The reason that we don't or haven't used atom economy alone is because it doesn't include the stoichiometry and it doesn't include the yield. So many of you probably have heard of a measure known as Efactor. It was developed by Roger Sheldon and has been used, and he's published around this widely. It gives some great measures of green chemistry or of the wastefulness of industry. And you might ask yourself, well, who cares about whether or not you're looking at Efactor or mass intensity? And this is where it gets into the psychology. And coming from a company and industrial experience, what I can say is something magic happens when something becomes waste. Everybody completely forgets about it. But what they do think about is their starting products. They think about the materials that go into their particular process. So I would argue that mass intensity from a manager's perspective is something that we want to focus on, and less so on Efactor. So let's talk a little bit about mass productivity, very simple calculation. Again, the mass of the API divided by all the materials that go into your process. And again, don't need to spend a lot of time on this. I've provided an example, and you can take a look at this at your leisure. But what does it take to achieve a mass productivity greater than 1? What are some guidelines that we might use? So on the next slide, I've tried to show that. And reaction mass efficiency is greater than 25%, yields, so on and so forth. The point is that the fewer number of stages, the higher the probability that you'll get greater than 1, and you have to be extremely efficient in your reaction mass efficiency. This may sound easier than what it is. We focused a lot on mass, but mass is not the only measure, and materials of concern are clearly something that we need to be focused on. There's a laundry list here that I've given that probably many of you are familiar with. The point is we need to identify these things and develop the strategies to eliminate or substitute these materials from our routes and processes. That takes us to the next poll, and I'll turn it back over to Bob.
Thank you, David. So for our final poll in this presentation today, please answer the following question. I use life cycle assessment in my work. The choices are regularly, infrequently, never, I've never heard of it, and don't have a way to do that. And please pick one. The poll will close in 5, 4, 3, 2, 1, and the poll is closed. And our results are quite scattered here, David. Regularly use it, about 21% of our audience. Infrequently use it, about 30% of our audience. Never use it, 22%. Never heard of it, 14%. And 15% say they don't have a way to do it. So back to you, David.
Thank you, Bob. And that is probably, in terms of regular users, is a little better than what I would have expected, but the remaining results is pretty much what I would have anticipated. For those of you who don't know about life cycle inventory assessment, this is just a graphic showing you the big picture. And really what it is from looking at how you have a chemical tree or a process. It starts out from raw material extraction, and it goes all the way through to final consumer use and end-of-life considerations. And you look at all of the material and energy inputs and then all of the emissions out of it. It's a methodology that's been around for many years, and I would say that unless people use life cycle on a regular basis, you can't possibly green your processes. So I'd encourage everybody to use life cycle. So what are some of the opportunities that we have? Well, clearly in the development process area, we need to be able to look at chemistry, engineering, innovation, second generations, increasing recovery from mother liquors. From a standpoint of engineering, we've got a lot to do in terms of mass and energy transfer and integration, separations, crystallizations, reactors, process intensification, so on and so forth. A tremendous amount that we can do there. Next, we need to think about the chemistry. I think that we need greater attention about the kinetics, route design, and alternative chemistries. And clearly one of the up-and-coming areas is around bioprocessing and synthetic biology. Clearly we need to do more there. And lastly, we need to come up with better ways of making our materials. We have too many hazardous materials. We need to do a better job at solvents, and we need to do a better job at renewable feedstocks. So some ideas here that innovations are needed everywhere. So in the laboratory, clearly we need to get to a point where we're using continuous processes and we have plug-and-play types of equipment. And we need to be able to do chemical property and kinetic measurement capability on the fly. And we need to be able to do that and look at it in real time. We need to think, as chemists, we need to bring more of an engineering mentality in, particularly around process chemistry. So we need to think about not just the whole route, but the whole process. And that might mean that we need to communicate a little bit more, and we need to change the way that we develop and optimize our processes. We need to think more about business processes and the business processes that overlay our technical ones so that we can build these in. And I would argue that in large companies where you're handling a lot of products, you really need to take a portfolio view. Just as we did in the chemistry to take a look at the portfolio view of chemistries, you need to do that in a product and look at greening things across the portfolio. And you need to make those technical decisions earlier. Lastly, we need to have other resources, money investment to change. That's where perhaps government comes in. We need equipment, time, and information. Clearly, we need to have better software and modeling tools available to us. So, clearly, assessment of greenness is a multivariate problem. If we try and just regress a single problem, it's never going to help us truly understand what's green and what isn't. We need to be able to engage communities and influence them early during development. We need to be able to green our metrics and understand that they help project teams. They should include a life cycle assessment. They need to be collected for every compound. They don't tell the whole story by themselves, and therefore they should be drivers for innovation. Lastly, I'd like to just very quickly acknowledge some folks that helped me out in developing the metrics in this presentation. And lastly, I'd like to open the floor up for questions. Here's a couple of books that folks might want to refer to: Green Chemistry Metrics and Green Chemistry and Engineering, plus other publications clearly are available. Lots been published in recent years. And now I'll turn it back over to Bob for questions. I apologize again for the audio and appreciate everybody's patience.
Well, thank you very much, David. Despite the audio glitches, I think it was a fascinating presentation, and I could tell by some of the comments that have come in that people really appreciated the materials. And, of course, I think John will remind everyone that you will have access to these materials shortly through the webinar website, and he'll cover that at the end. So I'd like to start with sort of a general question that's come up, and it went like this. When do you think we will start to see some of these green chemistry metrics show up in scientific journals?
Great question. And, you know, probably 4 or 5 years ago, we were discussing the need to have the editors of journals begin to require that as people make their submissions, that they use these kinds of measures. And I know that some discussions along those lines have been had. I can't predict, honestly, when there is going to be greater pickup, but I truly think that one of the biggest motivators, if you will, is if editors do require it and these things do come into place. I'd like to think that within the next 5 years, we have more than a few journals that are clearly making use of green chemistry measures, and that's really my hope.
Well, thanks, David. I will make an observation that one of our listeners sent in a comment that says he thinks that these some of these green chemistry metrics are already starting to show up in the peer-reviewed literature, and that's great news. Our next question is as follows. I will receive my PhD in inorganic chemistry in December. Do you need to have a, quote, green chemistry background in order to pursue a sustainability or green chemistry career?
Absolutely not. Great question. As I said at one point, maybe early on through the presentation, that green chemistry and engineering is a mindset. It's how you approach the problem. And I would argue that green chemistry, despite widespread perception in the broader chemistry community, it is good science. It's actually the best science. It requires people to think about the impacts of their materials, the impacts of their process, their route design, so on and so forth. And virtually anybody can make that transition. You have to use the right tools or become knowledgeable, but clearly I look forward to the day that chemistry curriculum isn't taught like green chemistry is a separate discipline. It should be integrated into virtually every chemistry and every chemical engineering course that's out there. It's just the right way, the best scientific way of approaching chemistry. And what's at stake is the very, civilized society. We've got to change the way that we're doing things, and this is an imperative.
Thank you, David. Another question. How do we weigh the different aspects of green metrics for overall comparisons? For example, if something is more energy efficient versus products that use green feedstocks or materials that are more durable versus biodegradable?
Oh, amazing question. Thank you for that. Really good question, and that points up a dilemma that you constantly face when you're talking about sustainable or green chemistry, and that is the notion of trading impacts. So as you pointed out there, which is better? Better energy efficiency, or less mass intensity? Do I want to have less of a carbon footprint in my supply chain? What I will say is that those are questions that ultimately lead to the values of any organization, and indeed your own personal values. And I'm sure that many companies have key performance indicators that they're evaluating their sustainability. And so the answer is many times is already chosen for them. In the case where it's not chosen, what you want to do is to use it as a multivariate optimization problem. By that I mean try and do the best you can with all the different measures that you have. Because you are going to have hazardous materials. You are going to have one part of the process that might be more energy efficiency. And you're going to have to trade it off. The question is, can we do the right impact trading to come up with the minimal impact overall across the life cycle and across the value chain? That's really where we need to get to.
Thank you, David. I do want to observe that we have quite a few questions coming in, and I apologize because we're not going to be able to get to all of them. So, David, if you could be quick with a few of these, maybe we can catch a few extras before the call ends, because we are going to honor our 3 o'clock time commitment. The next question is, I was curious about the point that you made about the need to fill in missing data. What exactly were you referring to, and how can that be remedied?
Well, that's why legislation like REACH has come along. And REACH has come along to fill in the missing data. And that was the driver in the TSCA regulations, or the desire to change them. And again, data is missing. It's up to companies to produce that data. There's a lot of interest on the part of customers and the community at large to take out hazardous materials. And that's clearly something that's going to happen. That's what I mean by missing data. There's also missing process data. Many times people don't collect all the data they need to make the right decisions.
Okay, thank you, David. Another quick question I think here is there a chance that the GSK Flask tool becomes publicly available, or the life cycle assessments of most commonly used reagents from cradle to grave?
Yeah, I know that my colleague, former colleague, Conchita Jimenez-Gonzalez, has an ambition to have those discussions with the Green Chemistry Institute Pharmaceutical Roundtable. And I would hope that Flask would become available in some form or fashion in the future.
Great. Next question. Are there organizations who can do life cycle analysis of new compounds or new processes that are developed?
Yes. There are a number of them. Sustainable Minds is one organization. There's a small startup company it was started out of MIT that advertises life cycles for $1,000. There are those, you just have to do your due diligence. If you want to get in touch with me, I can direct you to a couple different places.
Thanks, David. The next question is, what about economic metrics for green chemistry? Our customers in many parts of the world lean towards the bottom line and not how green a product is. Right.
So my answer is the best green products are green in terms of monetary matters. And I've got a lot of data that's shown this over a period of years, especially if you look across the entire life cycle of a compound. So it isn't an either or, it's a both and. Green processes are green and cheaper if they're designed correctly. And that's a big caveat, if they are designed correctly. And I think that if we don't go into this believing that we can make it less expensive and not sacrificing product quality or efficacy or how well it works, if we don't succeed at that, then we're not going to have a sellable product, and people aren't going to want to do it. So clearly, this takes us back to the discussion on design. We have to design low cost into our greening.
Thank you, David. I'm going to ask two questions sort of in combination here. The first is, experimental design is typically not taught in most academic institutions. Do the texts you showed discuss such issues? And parallel to that, what do you think about the iSustain tool?
Yeah, I think, take them in reverse order, I think the iSustain tool, which was a collaborative effort between John Warner's Warner Babcock Institute and SciTech Industries, is great. It's organized around the 12 principles of green chemistry, and I think it's a good start. I'm also I kind of grew up with design of experiment. I think we tried to introduce it. There's a lot of resistance to it in general among the chemistry community. I agree it's something that should be taught, and it's something that's an extremely powerful tool. And again, it's a great way of, if you do it right, of coming up with a greener route or end process.
Well, thank you, David. And to all our listeners, I know we haven't got to all your questions, but I see we are now nearing the end of our time. So, David, I'm going to ask you one last question. I will be teaching green chemistry to non-science students. I use educational resources put forth by the Warner Babcock Foundation. What about educational resources which focus on case studies? Any pointers?
There have been a number of case studies that have been worked on over time. I know that a number of business schools have tried to do this. I would say that in general, there are not a lot available in the public literature, and that's just one of the unfortunate things. There are a few, but not many.